Hey,
Hey,
hey.
everybody's here. Good morning.
Okay.
Good afternoon.
Oh, okay. Sounds good. So I guess I'll just go right ahead and start. Hey, Daniel. What's up? How are
Hey,
you?
nice to
Hey.
meet you. Yeah, good. How are
Nice.
you?
Okay, yeah, cool. Yeah, we'll get started right away. Hey, everybody. Welcome to another Saturday meetup session at the quantum computing meetup today. Today we have Daniel Claudino. Uh, his background, just a quick background. He got his Bachelor of Science at the University of St. Paulo, and then finished his PhD at the University of Florida. Go Gators! And now he's currently working as a research scientist at Oak Ridge Laboratories, which is related to a recent, I don't know if you guys watched the new Oppenheimer film, but it is mentioned that because at the Oak Ridge Laboratory, that's where they actually enriched the uranium and plutonium for the Manhattan Project. So interesting background there. Today, his talk, he will be discussing algorithms based on expansions of the powers of the Hamiltonian in detail, how they be cast completely independent from parameter optimization, how they converge to ground state, as well as how they can target excited states. He's going to show them specifically in applications in the areas of chemistry, material science, and condensed matter. So without further ado, Dr. Daniel Claudino.
Okay, thank you for the introduction, and thanks, Ellen, for the invitation. And well, given the introduction, I have nothing to do with uranium and plutonium enrichment. That being said, yeah, I'm gonna share my screen here. Yeah, so yeah, let's get going here. Yeah, the title was already mentioned, so yeah, I'm in just going over that brief introduction. Yes, I'm Daniel Claudino. I am a research scientist at the Oak Ridge National Lab, and I'm in the Computational Sciences Engineering Division. And within the division, I am in the Computational Science group. And today I'm going to talk about a technique that is not as widespread as some other current techniques that are used for quantum simulation, but I think it's promising, and I hope that more people become aware of it. So this is a few slides to motivate some of the results that I'm gonna show later on. So yeah, I mean, I'm pretty sure this crowd is tired, and I've seen thousands of talks with quotes from this talk that eventually became a paper from Feynman that he discusses the idea behind quantum computation. And I like, this is one of the excerpts that I like the most because it summarized the problem very succinctly. And I don't expect anybody to take the time to read this, but the gist of it is like, if you have several particles, they are all governed by quantum mechanics, and their interactions and position evolving time. So you have a lot of correlations that are very troublesome for our conventional compute machines, classical computers, to cope with. So he proposes here is that what if we come up with with a computer that is also itself governed by the same. So then we are on an equal footing. So yeah, so let's do it then. Like, we know the problem, we know how to do it. So why don't we just build this computer with its elements that obey mechanics and just use it to simulate all sorts of interesting things in nature, molecules, materials, solids, and so forth. And I think if people, like whoever is aware of where we stand on the state of the art of quantum hardware, we know that we have all sorts of challenges. So the quantum computer is not isolated from the rest of the universe. That means that the complete surrounding scheme can impart what you call a noise. This is just like an umbrella term that involves all sorts of different ways that skew your results, but it's, always in a bad way. And on top of that, so each gate, which is like some sort of like basic unit of to impart some change in the initial input. So each gate, like instruction, or like from a science standpoint, takes a certain time to be implemented. And so oftentimes you need several, hundreds or thousands of those gates to carry out some simulation task. And the more time it takes, then the more susceptible is your quantum computer to this, the effect of the surroundings. And the longest that your computer can endure this noise and still render some meaningful results is what we refer to coherence time. So we are tasked to come up with ways that we can get some meaningful answers out of the computer within this coherence time. Now, because of that, it opened the door to this like very active area of research that is called like hybrid algorithms. So the idea is like you combine classical and quantum resources, which the way that I see it, it's some sort of like heterogeneous computing, in which we are as a more software in computer science community, we are familiar with this, not in such an extreme way that we have like what we call it not only classical, but we have CPUs with GPUs and FPGAs and so forth. And this is one way that we can split the workload between these two sets of compute resources and make sure that we only delegate to the quantum hardware what it absolutely needs to do. So by doing that, we minimize the amount of dependence on the quantum hardware. And like I mentioned, GPUs, so we can see that as like some sort of accelerator within a mostly classical workflow. And this last part here is what I wanted to kind of basically start giving some crumbs to what I'm going to talk about, because hybrid algorithms are usually seen as synonyms with variational algorithms. And what I'm going to present today is an algorithm that is not variational. We're not variational in a sense that we have a parametrized quantum circuit, and then we are, trying to learn the vast combination of those parameters. Now, this is a little bit of cheap publicity. This is a software framework that we developed here at ORNL, have been developing for a number of years now. So everything that I'm going to present here is done with XACC, and it's open source. It's publicly available on GitHub. So everybody's invited to go and check it out and try for themselves and reach out with comments and suggestions. Now let's get to the meat of the talk. What are these expansions of the moments of the Hamiltonian? So it all goes way back to this Born-Weinstein theorem. So the basic idea is you're seeking a ground state of a Hamiltonian. You obviously don't know what the ground state is. And then you have a trial state, like a state that you can prepare, and you know what that state looks like. Now we know that the ground state energy, given the ground state is just this expression here, this Hamiltonian sandwiched between the Bryan cat. But interestingly, if we introduce this parameter t and then it goes to infinity, then we have this ratio here that converges to that ground state energy that we want, as long as that trial state has non-vanishing overlap with the true ground state. Now, we go from one, roadblock to another, because that only is true for this continuous parameter t when it goes to infinity. So we can't do that. But we can, there's several ways, infinite ways of expanding f. You can look at expanding the ratio here, you can even do, the Taylor expansion. And you see that now you no longer depend on this continuous parameter t, but then you can have all sorts of forms of this f that depends on all these different powers of the Hamiltonian, and t going to infinity corresponds to this n going to infinity. But if we decide to truncate this expansion somewhere, then we do that in a somewhat like judicious way. And then if we say if n goes all the way up to 2k minus 1, we say this is an expansion of order k. And so I just wanted to bring attention to this quotient here, and the fact that we can expand this in the powers of the Hamiltonian. So this draws several connections to other, relatively popular methods out there. So quantum power methods, Krylov subspace methods, imaginary time evolution. So yeah, depending on how you spin these expressions, you can get a different way of expressing it. Now, there is this thing that we call standard moments, which is simply that the expectation value of the power of the Hamiltonian for your chosen trial state. Now, there is this other way that we call a connected moments, which is this recursion, and then you taking those, you can go different paths. So you have this formula for an approximation to the ground state that we call the connected moment expansion formula, and there is different ways of doing this. This is this recursive way of doing this, which is easy to, or easy, it's at least like there's a closed form, and I don't put it here, but it's there's a way to tabulate all the approximations given different orders. Now, the slightly, or the other way that I'm going to show you that now depends on the standard moments is this, we call it the PDS energy functional. And the idea here is you have this linear system where you have for each element is given by one specific power of the Hamiltonian and a given index. Now, once you solve that system, you feed this polynomial, and then you solve for the roots. And what is pretty neat about this approach here is that if you decide you want an expansion of order k, then that returns the k lowest eigenvalues of the Hamiltonian. So it gives you bounds to the first k eigenvalues, the first k eigenenergies of the Hamiltonian. And just an interesting fact here is that if this PDS is truncated at first order, so you recover the widely spread variational quantum eigensolver. Now, a lot of what I'm going to talk about today revolves around solving chemistry problems. So this is a crash course on kind of the working equations in quantum chemistry. So that's why I call it quantum chemistry 3 slides. So we start from the molecular Hamiltonian, which considers all the interactions between nuclei and electrons, and the nuclei are assumed classical point charges, meaning we don't explicitly talk about the nuclear structure, protons and neutrons. Now we go one step further and introduce this Born-Oppenheimer approximation. So the idea is the electrons are much lighter than the nuclei, so they move much faster in a very different time scale. So we say for a given point in time, we can assume to a good degree of approximation. There's some instances where the approximation breaks down, but most of the time it holds well, in which that the nuclei are frozen as far as the electrons are concerned. So then we have this term here at the end that encapsulates all the nuclear contribution. So it's this simple classical electrostatic term that the nuclear repulsion between the nuclei. So we start solving this problem. So this is still quite complicated because we're talking about like a many electron problem. So there is two different ways of solving this basically. So there is one, people call it first quantization, in which you try to solve this explicitly. The other one is you include is like the spatial degrees of freedom in chosen basis, which is what we call like atomic orbitals and molecular orbitals. And so we assume that our molecule or our molecular orbitals are composed of atomic orbitals. Those are chosen, and then this one of the ways to solve for this is what we call Hartree-Fock. So it's like one type of in-field approximation in which we go from this expression to the left, which is solving many-body wave function, to having n one particle wave functions. So with which the solutions of this problem are your molecular orbitals, and the pseudo energies here are like orbital energies. So we do this, and then now we have to build the many-body wave function back up. So we do that by, we assume this form for our Hartree-Fock solution, and then we try to span the Hilbert space by including this terms that we call excitations. So we have single excitations in which we bring one electron from an occupied orbital to an excited or unoccupied orbital, and then we do the same thing. We can do pairs and triples and so forth. And then in this way, we recover that ground state when we consider all this possible excitation. So we span the entire Hilbert space, but then remember, we are constrained by how well that initial basis, the atomic orbital basis, can actually represent the problem. So we get the ground state constrained by that basis, and considering all this excitation manifolds is what chemists refer to as full configuration interaction. So we have all different ways of constructing this omega operator. The important thing is if you include all these excitations, then they all kind of converge to the same thing. Now, okay, so now that I gave some background, I'm going to start talking about this paper that we published a couple of years ago, which is how we move toward using this method and making it more amenable to hardware. So just a reminder here, so those expansions converge to the ground state energy as long as the overlap between the ground state and that trial state is non-zero. That overlap dictates how well or how fast you converge. So that means the overlap is not zero, but it's very small, then you have to go very high in the expansion, very the high orders of the expansion. So we don't want to do that. And so then we look into different ways that this method, we're presenting some bottlenecks. This is one way. Low overlap means high order for a given accuracy threshold, and that means a lot of measurements because each of those expectation values of the Hamiltonian require you to estimate a large number of Pauli strings. Now, the couple of questions that we try to address in this paper was, can we use these methodologies in an efficient way? Looking at molecular simulation, I mean, I decided not to delve into this matter in this presentation, although I said I would, but we've seen a few other types of Hamiltonians and treated them pretty successfully with this method. And then at the same time, so can we go beyond this mean field approximation, but still comply with the demands of the hardware such that you're still within what we call shallow circuit, that we see a significant increase in the overlap, that state that we're preparing in the ground state. So how we do that? So the idea is like I borrow this idea from another algorithm that is quite well known right now. It's called adapt VQE. So the idea is you set you define a set of operators that you're willing to work with, and then that can potentially span that the Hilbert space, that, or at least the subspace within which the ground state energy is located. And then once we define those operators that will span that subspace, we choose the most important one, maybe quote unquote most important one. So the idea is we see those potentially prepared states as different directions in Hilbert space, and it's kind of like a we just steepest descent, so just follow the direction which we have the steepest slope, and excuse me, and then we prepare this state by using the operator that was selected that way. And here we show that if we stuck with the mean field solution, this is a simple hydrogen molecule problem, and this is not in scale, but I would say this range of different distances between the two hydrogen atoms is very representative of the different ways in which you have the electrons behave. So we see that the Hartree-Fock, the mean field solution, presents like for smaller nuclear distances, the overlap is fairly decent, but then it goes down pretty rapidly. And then when you start stretching that molecule, you see that the overlap is overlap with the ground state is quite small. So that means it would require going much higher in the moment expansion. Whereas by preparing this new state, with this single many-body rotation away from the mean field solution, we see that the overlap is still fairly significant, very close to, meaning that state we're preparing is significantly closer to the ground state. So an example here, we take a look at the hydrogen molecule with a relatively, I don't remember off the top of my head the size of the Hilbert space, but it was fairly, large for at least what we did a couple of years ago. And we see that the mean field solution, Hartree-Fock, is all the way up there. And this, remember that I said the ground state energy is given by this full configuration interaction, which is the solid black curve. And we see that if we try to keep our expansions in low orders, so PDS2 and CMX2, using that mean field solution as our trial state, we see that here around the internuclear distance region, which is dominated by that mean field solution, we see that this is a fairly good approximation, but as we start stretching the bond, we see that it's no longer well suited approximation to the ground state, and there is a fairly striking distance between what we get from these two methods and our deemed ground state energy. Now, if we only did VQE, which would be first order this expansion, see that it tracks the curve relatively well, and there is a consistent difference. And there is also in the middle around 1, we see that there is this kink of sorts there, which means which has to do with the fact that you're selecting different operators and you're not consistent in how you're preparing this state, and which means that you have the state that you're preparing that way is not balanced throughout. And what's kind of interesting is if we use this quote unquote like imperfect state and feed that state into both PDS and CMX, even at such a low order, we are spot on. There's very little deviation from the ground state energy. This is a quick comparison of this idea with this other variational algorithm, adapt PQE. If we were to follow adapt PQE all the way to reaching the same level of accuracy. So adapt PQE basically would take that idea of selecting the most important operator and do that in an iterative way until there is some stopping criterion met. So we see that this is, in a bit of background, this algorithm is often seen as a way to work around the bottlenecks of standard PQE. So we see that I think the most important plots here are on the right, where you see that we have a constant circuit depth all throughout, whereas the circuit depth involved in adapt PQE just grows, and it takes a while for the left here. It takes a while for that algorithm to catch up in terms of accuracy. Now, one of the problems that we were anticipating, at least in the beginning, was the fact that we would need a lot of measurements, a lot of Pauli strings needed to be estimated in order to estimate the expectation value of all these powers of the Hamiltonian. So, and then initially we naively thought, oh, it's gonna grow, exponentially. And as we start working on this problem, we notice that there is a point after which you don't see any new string that you haven't seen before. And that's when I came up with this idea of let's just measure them once and keep them and go back and forth so that we don't measure things that we need to do more than once. And once we do it, we cache them. So that means going back here, we see that for when n, which is the power level the Hamiltonian, is 4, which is like halfway between second and third order, that's when we exhaust all the strings that needed to be measured. So we come here and so this warrants what I call like free higher order corrections, which means everything past third order does not require any more fun resources, and there's like a trivial amount of classical overhead, like solving a polynomial, stuff like that. But so that's one positive aspect, which means once you exhaust the number of Pauli strings, then you can still improve upon your answers, even though you're not paying that price. And the second thing is PDS has some like built-in variational flavor to it, which comes from the way that the linear system is set up. But it's not, like I said, not variation in the sense that we have an underlying parameterized quantum circuit that we need to tune in the parameters until we learn the best combination, which is a good thing here because we see that the CMX one overshoots the energy, and sometimes it's or most of the time it's not good because we like bounds. We like to know that we are not overshooting the results. Okay, so this is how we can go even further. So the idea is can represent any power element. Hamiltonian is like this generic, sum of weighted Pauli strings. And then the Pauli strings themselves, their expectation value are between -1 and 1. So we can use this fact and ignore Pauli strings that are weighted by very small scalars right here. So I just pick this square geometry and ran some experiments with different thresholds in terms of keeping only a certain fraction of the Pauli strings, and for different thresholds here on the right, and we see that there are some very aggressive thresholds in which your operators are no longer Hermitian, so they are not an observable, so they destroy that property. But sometimes you can, the sweet spot here would be to keep it at low orders and to ignore as many of those as you can and still be relatively close to the energy value that you're seeking. So see that for 10 to the -1 or -2, you're still very far. They're like huge errors, but as that becomes more conservative, we get better and better. And just zooming in, we see that 10 to the -5, which means both the scalars CI that are below that threshold are ignored. And for smaller low orders, look here on the left, then we see that saves about 25% of the entire measurement schedule. I mean, it may not seem like a lot, but we're talking about thousands or tens of thousands unique Pauli strings, and each one of which has to be run for sometimes thousands of shots. So these things they build up, and at the end of the day, you're saving millions of circuit implementations. So to wrap things up here, this part of the talk. So one of the conclusions is that this idea is like we can reach a very significant degree of accuracy without deep circuits. So sometimes you have to pay the price by doing more measurements. So I think we can circumvent this or alleviate this to a large extent by coming up with these simple ideas that we can ignore some things that are not important, or keeping track of the strings, so only measure them once and things of that sort. And with this experiment here, this problem, we noticed that this PDS expansion, by virtue of being, having this variational capability built in, is preferable over CMX. Now, this is a more recent study that we did with these expansions. And we looked into a more material science like inspired problem, which has to do with the phenomenon known as singlet fission. So the background on singlet fission here is it's motivated largely, or at least much of the research that is done right now is spurred by solar cells, and it has to do with the fact that to have a standard single NP junction solar cell, the efficiency is bound by this Shockley-Queisser limit, which means you get about 30% of your incoming photons being converted into charge carriers. Now, with the singlet fission approach, this efficiency goes, at least theoretically, can be all the way up to 200. So that's a huge improvement. And but in order to realize this, there is a very peculiar kind of energetic requirement that you need to fulfill, which is you need a coupled spin singlet species, and then in such a manner that the first triplet state, the energy of the first triplet state, is roughly halfway between that couple spin singlet state and the first spin singlet excited state. So this is some sort of like energy diagram. So the idea is like once you fulfill this, then one of the species would be excited to the first excited state, and then there's like internal conversion of that excess energy, and you end up with the two species in the triplet state. Now, from a theoretical standpoint, looking at the kind of the electronic and the excitonic structure of this problem. So that first singlet excited state is dominated by what we call doubly excited determinants. So the idea is if you start from a mean field solution, that first excited state is mostly composed of double excitations, double rotations away from that mean field solution, which means that mean field solutions or single particle theories, they're more or less here, Hartree-Fock and density functional theory and so forth. They are not cut for this sort of problem. So they are not able to handle the underlying electronic structure of this problem. And it's some sort of a, it's well known that to be able to understand doubly excited determinants, we need triple excitations in order for the double excitations to quote unquote relax the presence of high order contributions. So the typical method to handle this triple excitations is this ugly huge acronym, but bear with me. What is relevant here is that we need those triply excited determinants out of the mean field solution. Now, so the idea is like we looked into, well, in the literature, it was found that this kind of molecular prototype here, the H4 molecule is a simple system that complies with that energetics of the underlying singlet fission phenomenon. Now, the dynamics that is involved in singlet fission is much more complicated. So I'm not going to talk about that specific problem because it's not even there's no consensus in the literature. But looking at the energetics here, so there is a range of distances between each of those neighboring hydrogen atoms from which you can still satisfy singlet fission, and then for sake of simplicity, we just kept them all equally distanced. And we start from this that mean field solution Hartree-Fock that I mentioned before, and we map, we did this for the previous problem as well. We go from fermions to spin operators through the Jardo-Wigner mapping. Now, this is a bit more of like formalizing what I said, and it's a little bit, there's a few things that we learned between that first paper and this one, but so the idea is like, I have a generic observable. Again, we know in terms of spins, this is how they comport, and then we have n moment of the Hamiltonian. Just put the primes there, but they all follow the same generic form. Now, we notice here that those Pauli strings P, they're not exclusive to any individual moment operator. So, and we take advantage of that to only keep track of the unique strings, so we don't measure things more than once. Now, this is for this problem. On the left here, we have the number of unique strings, times 1,000. And something that was quite unexpected is that you have this plateau between order 3 and order 10, and after that it starts ramping up again, even though there is no you know, significant energy improvement. And we can see that because keeping track of the energies in each of these 3 different states that you have to account for in singlet fission, we see that by order 10, they are all converged. So we don't see any more energy improvement. So this was done in a numerical simulator to keep track of the, the resources that we need. And so this tells us what we can, anything that we do between order 3 and 10, costs the same. So we might as well go to order 10, all the while we are converged, the energies are converged within, in terms of the expansion order. So that's why we decided to do. So we go to order 10. Now, I'm going to mention this later. We did this experiment on the Hamiltonian H1-1 hardware, and we don't have a lot of time, and they keep tracking the different ways of credits, but they don't give out a lot of credits, so we had to be really smart. So one of the ways that we approach here to go even further in terms of saving on resources is this idea of qubit tapering. I don't want to dwell on it too much, but the idea is you have your Hamiltonian, then you transform it, like you just rotate it in such a way that now you have this H prime, and that H prime lives in a subspace of the initial Hamiltonian, and everything outside that subspace is just a product of simple Pauli matrix operators. So then you only have to deal with the H prime in that smaller subspace. So in a graphical representation of that is this one. So that's one way that we can approach the problem and save some resources. Another way is to realize that we have a huge number of Pauli strings, and there are many ways in which they commute. This is not the most stringent, general way, but this is a simple way, is to check the qubit-wise commute. So qubit by qubit, you check their spin operators, and they commute for all of them. So that means the qubit-wise commute. So the idea is we map this onto a graph and use graph techniques to find larger chunks of the graph that are all fully connected. So, and that's equivalent to a very well-known problem in CS, so the minimum click over. So we do that in order to, and then we find a rotation operator that rotates. Once you find all the portions of the graph that are fully connected, so that means all these Pauli strings commute. We find a rotation operator that rotates the state onto the basis that are the eigenbasis of that operator. So that means all the operators within that group share the same basis. So we need only to measure that rotation operator instead of all the commuting Pauli strings. So once you do that, then we kind of trace it back to the individual the expectation values of the individual strings by doing this here on the bottom, which is pretty standard. And then on top of that, we develop this parallel circuit implementation approach. So we use this hardware that I mentioned, this ion trap system, and we only did 500 shots. The hardware is really clean, not a lot of noise, so you can get away with low hundreds number of shots most of the time. So with the qubit tapering, we went from an 8-qubit problem to a 5-qubit problem. And given that this hardware has 20 qubits, so we were able to implement 4 simultaneous state preparation and measurement protocols. Now we end up with this like huge, 20-bit strings that we have to decompose and trace out each degrees of freedom kind of individually, but it's much easier to handle than having to cope with constraints of the hardware. So this graphics here is just a pictorial way to represent what we did, all these like multi approaches. And originally we had for the singlet and the triplet manifold the same number of value strings, almost 8,500. Applying the qubit-wise commuting technique, we brought it down like about an order of magnitude. If we went back to the original 8,000 and so, and only applied qubit tapering, get more or less the same number of savings. If you combine the two, then we get down to about 160, 70 something. And then if we apply all of them together, then we went from 8,500 give or take to 48 circuit implementation. So this is the main takeaway, I'd say, from this paper, is that we have this CC, this couple cluster method, which is the gold standard of electronic structure. So we see that if you only include single and double excitations, we are very far from the exact, which is the dark red. But if we in the the community understands that if we add up to triple excitations, then that's enough. We see that it's not for this problem, and we see that our approach is the one that gets closest to the exact numbers. So there is a little discrepancy here in the S1 state that I'm going to discuss a little bit moving forward. So this is, I'm not gonna dwell on this too much, but it's to show that this is the distribution of probabilities over different determinants or different computational base states, and see that they are quite different, and they give different weights, or they favor some states that shouldn't be as favored. Now, we looked into some error mitigation to see if we could bridge that gap or bring that S1 energy a little closer. So this is a pretty standard, readout span error mitigation. Now, with this hardware, if you perform a final measurement and you have no crosstalk, we took advantage of that, and then one step further and decided we're not gonna consider correlated errors, which is a consequence of that. Now, Continuum reports only a few ranges of errors, as opposed to something like IBM where they give you errors per individual qubit, which is different here because ions are all equivalent. So they don't have it too technically. So then this S matrix here is the single qubit readout error probability. So we can tensor it now because we don't have errors, readout errors that from one qubit affect another. So that A matrix is just the tensor product of one qubit, quote unquote, like error matrices. And we can invert the matrix because each inverse of the A matrix is just the inverse of each one of those individual S matrices. Then we error mitigate our initial probabilities like this. And then I mentioned the sparsity here because so in principle, yeah, we would have to consider 2 to the 20 bit strings. And then if you were to do this experiment with correlated errors and everything, so this is how many strings would have to measure, but luckily we don't. And we do this and we renormalize the probabilities. And this is what we found. that there is very little to be gained by mitigating the errors. And then this is the first table tells us, and then the second table tells us I ran some state vector simulations, and I realized that that error is actually coming from the fact that we are measuring a 20-bit string, so it comes from shot noise versus readout. So and that's something that we would have a hard time working around here because of the constraints of access that we have to the hardware. Now, to conclude here, yeah, so we realize that moments expansions, and in this case, I can only speak to this PDS, so that's effectively handling that complicated underlying excitonic/electronic structure that gives rise to singlet fission. With this combined approach, we observe 2 orders of magnitude reduction in the number of circuit implementations, so making it, even with the stringent constraints that we had access to the hardware, still get this experiment run. And that error is largely, it's one of the side effects of doing this, which is because we are sampling a much larger space. So these are all the people that I want to thank for working with me, and funding that comes from the Department of Energy and the facilities that give access to the hardware that we use, and everybody for making it Saturday of a long weekend. I'm sure you had better things to do. Thank you.
Cool. Yeah, thanks, Daniel. Thanks for the talk. Yeah, so I guess that's it. Just wondering if anybody had any questions. There was just one question in the chat during the talk. I don't want to disrupt you though. It was on YouTube. I think in one of the slides, you did mention it's someone asked why it says T0 instead of T1. It's in the singlet fission slides.
Oh, okay, yeah. This is I'm going against the grain here a little bit because this is just a matter of convention. Some people don't like to label that triplet, and most people don't really. That first triplet state as T0, they label it T1. I guess this is where the confusion comes from. Yeah, so and conventionally, if you read singlet fission literature, yeah, most of the time it's not T0, it's T1.
Okay, thanks for the clarification. Just another question that was in the chat. Someone was asking if you can explain PDS again.
Oh, okay. Sure. Yeah, so to start here, I said we have infinitely many moments expansion. So there are many different ways that you can combine those moments, the powers of the Hamiltonian, in such a way that you get it in approximation to the ground state energy. Now, something that they all share is this quality here. Let's put it that way. This constraint that if you say it's order k, then we need to evaluate 2k minus 1 Hamiltonian power elements. Now the PDS here is, so you still do that. So if you say, well, I want say PDS2, so then you have to do h and h squared and h cubed, and get the expectation value of all these powers of the Hamiltonian. then you drop them into this matrix M and the vector I, and then you solve this linear system. Find x. And once you find x, then x are the coefficients of this polynomial in this variable beta or whatever. I don't know why I picked this. this letter here, but this is, and then you solve or you find the roots of this polynomial. And those roots are upper bounds to the first k eigenenergies. So if you say I want to do PDS2, then you have to, again, h squared h cubed. That gives you two roots. So an upper bound to the ground state and an upper bound to the first excited state. Hope that answers the question.
I think that does. I think it responds back. The next question is just kind of putting in a bunch of questions. I guess, like, do you have like a link tree or something? Because a lot of people are asking for any links to your presentation or slides or background research papers, like GitHub resources. Like, do you have like a link tree or something like that? Or
Well, I don't right now. I mean, I can put something. The presentations are not on GitHub. I mean, if you give me a couple of minutes, I can share the links with those papers.
yeah, I just think that people are just interested in taking a further look.
Yeah, sure.
Yeah, so I don't know. You could just do that later or whatever,
Right.
and me and Helen can just send like an email.
Okay.
But like, yeah, so we could just do that or something.
Right.
Yeah. So yeah, I don't know. Did anyone else have any like other questions? Just drop them in the chat or just hop off mute and just ask away. But if not, I guess.
Yeah, I have some questions.
Oh, yeah, Idamar's hopping in. Hey, Idamar.
Hello. First of all, your handling of errors was very interesting and very, very non-deep question is, can this be used to error code algorithms, error correction codes?
I'm going on a tangent here, and I mean, okay, the short answer is that I don't know. I mean, I don't think I know enough of one-way error correction to give a definite answer. Yeah.
Okay.
Sorry.
The other point that is showing my ignorance, can you go back to this ground state?
Where?
You had a slide about ground state at the very beginning. And my wonder is, we are talking here about molecules, right?
Yeah.
So maybe you can elaborate and explain to me. It says full configuration interaction between the what? The two molecules or the degrees of freedom?
Oh, okay. So we call each one a, okay, so when I say up here lat like this thing here, this you can see as a computational base state or something like that. We call each one of those as a configuration. So it's an electronic configuration, like in terms of you can encode different symmetries, but usually we do that in terms of a particle number. So we order the orbitals. Each element here is an orbital, and then if it's 1, then we say it's occupied. If it's 0, say it's unoccupied. Now, when we perform those excitations, so you generate different, what we call electronic configurations. So there is a family, a hierarchy of configuration interactions, which means, what and how of those configurations are you incorporating to approximate your energy spectrum. Now, the full configuration interaction is like, yeah, you consider everything, all the possible ways that you can make configurations, meaning all the possible ways that electrons can occupy different orbits.
So is there assumption here that all participants in this interaction, chemical interaction, all of them should eventually reach ground state?
No, you find a ground state for an entire system, right? Now, if you're saying, and there are methods that built upon, I think that's what I'm getting. You're conceptualizing here. It's like if you have, say, fragments or molecules that are far apart, or even like atoms, then to use the ground state of each one of those subsystems as to compose the composite system. So you can do that, but then once you apply this, you apply to whatever system that you chose. So it can be the molecule, or if you isolate an atom, it can be the atom, or whatever else.
Okay, thanks.
Right.
Cool. Yeah, a couple of questions in the chat. Actually, Dave Chapman, how much of this has been done using quantum hardware as opposed to simulators?
Yeah, I mean, the first problem here we did I didn't report anything on hardware. It was mostly simulator. The first paper, I did very little with hardware, but nothing that we published. Like the second one was, the main results are all done on that Quantinuum hardware that I mentioned. Now, other than what we've done, I think there is a group in Australia that they work with a slightly quite different expansion, but still within this realm of Holmes expansion that they have done. I think they work closely with IBM, and they have I'm aware of one paper that they do some simulations on the IBM hardware. That's all that I'm aware of.
I had a quick question. Excuse my ignorance on this topic. So for your Hartree-Fock calculation, you are simulating in the ground state, and your moment excitations is trying to encode information using excitations. Does this account for any of the entanglement states that you can get in quantum information? And are they stable?
Okay, so yeah, those are interesting questions. So the first, yeah, so the thing with this, so there are several mean field approaches. So what is distinct about Hartree-Fock, there are others, like I said, is that this is the one that minimizes the energy. So it's like the variationally optimal mean field solution. So yeah, we are shooting for the ground state when we do Hartree-Fock. There are other ways. There's like time-dependent Hartree-Fock and other ways to target excited states. But this is not what we are doing. And the double excitations. So double excitations, yeah. So that's in a way, yeah. That's how we account for entanglement, because you put your system in. That's how we put the system in a superposition of a bunch of computational basis states. They're all entangled.
Okay. Yeah, so Ron had a question. Ron, did you just want to unmute and ask your question, or?
Yeah, I was wondering, Daniel, if you had any references to material that helps people take these formulas from Hamiltonians to actual code, whether or not you're running it on a quantum machine or not. Like what does what's the best way to or in code represent a Hamiltonian, for example?
Oh, okay. Yeah, I mean, there is this software that I developed, XACC, so that's in C++. We have a bunch of, most of the code is exposed through high binding to Python APIs. Now,
And that code's up in the GitHub thing that someone posted? Okay.
Yeah, GitHub, yeah.
Great.
So there, I would say Open Fermion from Google is also a pretty decent one for handling like fermionic Hamiltonians. It's pretty straightforward as well.
Okay,
Those
great, thanks.
Yeah, okay, yeah, you're welcome.
Yeah, just to follow up on Ron's question, Daniel, like GitHub, Eclipse, SACC, XACC, that is the GitHub page, right?
Yes, correct.
Okay, sounds good. I just want to confirm that because somebody else posted yeah, so I think that's all the questions I see in the chat. Did anybody in this meeting have a question they want to ask? Don't want to unmute, anything like that? No, 3, 2, 1. Okay.
Hello. Not sure if, can anyone hear me?
Yeah, Anna. Yeah, we can hear you.
Yes, I just wanted to introduce myself. I'm Anna Ginsberg. I'm the director of the Blockchain Center, Bitcoin Center in New York City. And we were hosting the quantum computing meetup. And I would love to do an event with you guys to do a presentation. And also I wanted to comment on Michael's question. And he actually brought up a great point because I realized that the IBM's quantum computer uses Qiskit and that uses Python. So would there be a way that you would be able to create a code library to incorporate these algorithms more easily used in Python? And technically, IBM gives us free quantum computing credits. So as soon as we're ready, we could actually use their quantum computer to figure anything out. So
Yeah, I would say. Yeah, well, that's a great question, and I'm gonna take this opportunity to publicize XACC even more because the cornerstone of XACC when we came up with the idea back in 2017 was to make it hardware agnostic. So everything that I show here, if I give you the code, you need to change a string. Like you need to go from Honeywell, because we still use the interface that we coded up back when Quantinium was called Honeywell. If you change that to IBM and IBM colon the name of the hardware, meaning IBM Osprey or something, that's the newest one, you don't have to do anything else. It's all done in the backstage. So we took upon ourselves to code up all the transpilation, compilation steps and everything else. So from a user standpoint, you don't have to do anything other than knowing the name of the computer that you are targeting.
wow, that's incredible. That's awesome. So basically you're saying all we have to know is just recognize the hardware that's being used and it will automatically adjust.
Yes. That's
wonderful. And what do you think, like if I were to host a hackathon and try to find people, and coders that would be able to create new algorithms and find applications specifically for this model so that we can have real life problems being solved using this solution?
Yeah, no, that would be a lot of fun, I think.
What are some of the applications that you can come off just like right offhand that we could be using something like this for?
Yeah, I would say the right now there's like the rising. There's a few use cases of that you were mentioning here, one-way correction, and let's say the bottleneck that we are seeing is quantum compilation. So quantum compilation is something that's becoming really important to do compilation in a robust manner on the fly. Because for a lot of advanced one-way correction approaches, you need to run your algorithm and decode that algorithm in real time, such that your algorithm can proceed knowing that outcome of the first measurement. So this is one example of which, but I'm pretty sure if I ask my colleagues here, because we are in a computational science group, that we can come up with a whole slew of interesting and challenging applications.
And I apologize for my ignorance, but how many qubits would we need to be running this? And was it possible to just use classical computers? So for example, like if you need 16 qubits and we can't reach that, could we use 15 bytes and then 1 byte, kind of like to do it in 2 steps on a classical computer?
Well, I mean, that starts getting into what I said to one of the other participants. That's like, I don't know enough of the nitty gritty that goes behind error correction to comment on it. Like I've seen some experiments continue without a paper. It's not a quantum error correction as such as what I call quantum error detection. But it's still fairly advanced because it uses an algorithm that's called phase estimation, which is deemed like impossible for near-term hardware up until they had this application. So yeah, but then in terms of actual implementation for some of these problems, some of the precise requirements, then I think that's a little beyond, beyond me and my level of knowledge.
Great.
That's very humble of you to say.
So if I could ask another question, you said you were using Quantinuum's trapped ion resources. Were you interfacing through their bracket framework, or are you going straight to hardware from your stuff?
Well, when we did this, we were targeting the machines directly. I talked to one of their, managers, they call Ticket. Bracket is from Amazon, I think.
Yeah,
yeah. So I was talking to Catherine. So she is one of the leads,
Catherine Spendier. Yes.
Yeah. So I was talking to her last month, and she told me that right now, because the experiments that we performed for this paper, we ran late last year, but right now nothing goes to their hardware without going through Ticket. So I think if I were to do it right now, it would probably go through their software. But when we did, like, there wasn't this middleman, so it was it was up to us to kind of compile the right way and make sure it worked.
So have you considered writing an importer to their I guess it's their PyTicket framework?
Well,
are you generating code? Your code is in your framework, or are you using Qiskit-like or just generic quantum? Quantum language.
Yeah, we have our own language / intermediate representation, which is but it's like as with any other intermediate representation. So at some point in the workflow, we need to know the structure, the type of data format and stuff that the backend we receive. So right now it's all like cloud servers and stuff. So we have to we do all the HTTP communication with the cloud server, and then for each one of those specific hardware backends, we know, if it's like IBM, we need to send them CASM strings, open CASM to, and if it's other hardware like Rigetti has their language will, so we have to convert, compile that our intermediate representation to will. Now to go back to your first question, we don't have any, immediate plans to interface with Ticket now, mainly because we haven't, needed to do that. Now that they said everything goes through Ticket, maybe next time that we want to use their hardware, maybe we have to.
Hello.
Yep.
Well, very cool. If you need somebody with compiler writing or transpiling expertise, check me out. I assume they want you to go through there to use their optimization routines before it gets to their hardware.
Yeah, that's what I got from Catherine. Yeah, that's think that's
Very cool. Thanks.
Yeah. Well,
Cool. Okay, another question in the chat. How is XACC handling the data loading problem for hybrid quantum classical architectures for solving quantum machine learning problems?
we did a couple of machine learning experiments way back then, and yeah, I would say that one of the, because XACC is basically just a framework, so it depends on the interfaces and the plugins that we add to it. Now, a lot of those plugins are like we ourselves develop. There are some people, there's like a small community that people who have developed their own plugins. So I'd say a full variational run of any algorithms like BQE or machine learning, yeah, it tends to be pretty time consuming because there's communication to the servers, and then depending on how they handle job submission, they have a queue. A job can sit there for a while, and then they send the results back. And once you do that, you have to process these bit strings, and depending on the post processing, if requires some elaborate linear algebra routines and things of that sort, it can be a pretty time consuming workflow overall. We don't have anything like right now. I'm not aware of any use cases like currently highlighted with XACC. So I'm not a QML expert myself. So I would say more broadly, the experience that I have with variational algorithms, that's the bottlenecks that I see, which I've seen apply to QML, but I don't have any present use case to kind of illustrate those things. Does that answer your question?
I guess I don't see anybody. Yeah. Oh, yes. Yes. Jordan says yes. Thank you.
Yeah, you are. Yeah. If I think the opportunity here, like I said, so the framework is open source, and so it's available, and we are very welcoming of contributions. So even if you feel like you're an end user and C++, it scares you away or anything, like if you come to us with an interesting problem for which we don't have the capabilities, but it's like within the realm of possibility, yeah, we'll be really excited to hear your use case and if possible, work with you to come up with a software infrastructure that would help solve that problem.
Great. Oh, yeah, I don't see. Yeah, Maja says it is a great framework. Yay. But yeah, I guess that's it. I guess that's all the questions. Daniel, thank you for answering all those questions. There's a lot of questions. Yeah, I guess I can wrap it up. Unless Helen, did you have anything to say on your end?
No, thank you for coming.
Okay.
Yeah.
Thank you for hosting, Helen. Yeah, so yeah, just a bunch of comments and just complimenting, great presentation. But yeah, before everyone goes for the weekend, for North America, well, I think Canada, I don't know about the US, it is a long weekend this weekend. So make sure you have a good time. Before everyone goes, just a reminder that there is another meetup scheduled for October 7th, Saturday, 1 to 5 EET. It's not going to be me moderating this one. It's Paolo Gora, CEO of Quantum AI Foundation, with Professor Vedral at the University of Oxford. So make sure to tune into that October 7th on Saturday, 1 p.m. EDT. And also just a big thank you to Daniel, Dr. Claudino for talking today at today's meetup. Yeah, Daniel, any parting words before we wrap it up, or?
Oh, I mean, well, thank you for moderating, Helen, for the invitation. Yeah, I had a lot of fun. I like the engagement. Guys, thanks for the questions. And yeah, I thought I had, I realized I didn't have a lot of information here, but it would be easy to find on LinkedIn. If you Google my name, you can find my profile on the Oak Ridge National Lab website. Should have ways to communicate, reach out to me if you have any questions, please.
Yeah, for sure. Yeah, if anybody has any questions, reach out to Daniel on LinkedIn. Yeah, that's it. Have a great weekend, everybody, and see you at the next meetup.
Bye, everyone.
Yeah, peace.